Alright, problem 1 on the study guide. We're supposed to use the definition of derivative to differentiate a polynomial function. Recall the definition of derivative says that f prime of x is equal to the limit as x of h approaches 0 of f of x plus h minus f of x all over h. So I'm going to expect to see the work involving that on your test. Basically what you're going to do is figure out f of x plus h, which just changes all the x's to x plus h's. So 2 times x plus h squared plus 3 times x plus h minus 4. That gives me 2 times x squared plus 2xh plus h squared plus 3x plus 3h minus 4, which gets me finally, simplifying f of x plus h as much as possible, 2x squared plus 4xh plus 2h squared plus 3x plus 3h minus 4. That's f of x plus h. According to this, we're supposed to subtract f of x. F of x is this. And f of x plus h should contain f of x. So if I subtract f of x from that, 2x squared subtracting from 2x squared, 3x subtracting from 3x, minus 4, subtract that, you get plus 4. So here's minus f of x happening. 2x squared minus 2x squared cancels, 3x minus 3x cancels, negative 4 plus 4 cancels. That leaves the top expression altogether, f of x plus h minus f of x, equal to 4xh plus 2h squared plus 3h. So now we're doing the limit as h approaches 0 of the remainder of this difference, which is, again, 4xh plus 2h squared plus 3h all over h. We can't substitute 0 immediately because h is in the denominator, but you'll notice in all four terms, 4xh, 2h squared, 3h, and h all contain h to the first power. So cancellation is allowed. 1h goes away there. H squared changes to h to the first goes away, h to the first goes away. That leaves me with limit as h is approaching 0 of 4x plus 2h plus 3. And at this point, if you substitute 0 in because we're not dividing by 0, 4x is fine, 2h disappears, and 3 is fine, so we're going to end up with 4x plus 3 as f prime of x. And just doing basic power rule, 4x plus 3 obviously is derivative of that, so we can verify that we did everything correctly there. It's going to be a polynomial function on the test. It'll work out similarly to that, so just practice simplifying the f of x plus h part. Again, f of x is going to subtract away, leaving a bunch of h terms. All the h's cancel, then you put 0 in. Number 2, calculate y prime. What we have here is a product of polynomial functions raised to powers. So I would do the product rule. I would call this function 1, I'd call this function 2, and then I'm just going to differentiate. So if I go y prime equals, if I do 1d2, that's going to be x plus 3 cubed as it is. And then d2 is going to be 4 times x minus 4 cubed times the derivative of x minus 4, which is 1. Then I got to do plus 2d1. So 2 is going to be x minus 4 to the 4th as it is. And d1 is going to be times 3 times x plus 3 to the 2nd times the derivative of x plus 3, which is 1. So there's the derivative. Again, that's the calculus of it. What's left is the algebra of it. And what I'm going to notice in this is that these two objects here, x plus 3 and x minus 4, show up in this work. And they have a common factor based on the powers. So for x plus 3, the powers are 3 and 2. I'm allowed to take x plus 3 squared out. For x minus 4, I've got 3 and 4, I can take the 3 out. So you always, when you look for a common factor, you can take the smallest power out. So next thing I would do in this problem is I would write x plus 3 squared times x minus 4 cubed. That's the common factor that I'm extracting. And then I got to write the leftovers in this. I'll put a bracket here to represent that. So if I'm taking x plus 3 squared out of x plus 3 cubed, that leaves x plus 3 to the 1st. The 4 is not being affected by all this. I'm taking x minus 4 cubed out of x minus 4 cubed. That's gone completely. And then times 1. Put that just for effect. And then the same thing on the second term, plus begins the second term, here's the second term. I'm taking x minus 4 cubed out of x minus 4 to the fourth. That takes 3 of those 4, so there's 1 left over. And then there's a 3 that's not being affected by this. We're taking x plus 3 squared completely out, so that's gone. So that gets me to this point. The green and the black are perfect. The blue has to be fixed now. And all they have is this, this is to the first power. I don't need the first really up there. 4 distributed through here is going to get me 4x plus 12. And 3 distributed through here is going to get me 3x minus 12. So that ends up getting me y prime for a final answer. I'm just going to bring this stuff down. So x plus 3 squared times x minus 4 cubed. And then 4x plus 3x is 7x, 12 minus 12 just happens to cancel. That's coincidental. That's not a guarantee that will happen on the test. But this simplifies to something. Get that simplified to whatever it simplifies to. And I'm looking for a final answer looking like that for that problem. Number 3, this time we have a quotient. It doesn't look like it's easily changed into anything but a quotient, so I'm just going to go ahead and do it as is with the quotient rule, which if you recall is low d high minus high d low over the square of what's below. So high 2x, low 3x minus 2 square root. So first thing I would do, just a little bit of algebra to make this easier differentiation. Fractional powers are better than radicals when we're differentiating. So when I have to do d low, it's better that it's in a fractional power structure. So if I go y prime equals, if I do low d high, low is 3x minus 2 to the half power, as is. D high, the derivative of the top is just 2. Minus high, 2x as is. D low is the derivative of the bottom. This is a object to a power, so the chain rule has to be used. So I'm going to do 1/2 the power times 3x minus 2 to the negative 1/2, 1 lesser power, and then 3x minus 2's derivative is 3. Okay. So 1/2 times 1 base to 1 lesser power, derivative of the base 3. That's how you differentiate. So this in this box here is the derivative of the bottom. This box is derivative of the top, and that's all the calculus that happened in this problem. Okay, all that over the square of what's below. So if I square this thing to the second power, 1/2 times 2 is 1, so I'm just going to get 3x minus 2. For the first, if you want to get really technical about it. Okay. Next thing I would do is I start beautifying this thing up, making it look prettier. 2 times 1/2, the 2's cancel. So I'm going to go y prime equals. Now at this point I'm done doing calculus, I'm going to go back to radicals instead of fractional powers. So this first object, which I'm going to use some colors here, this is my first term. I'm going to get 2 times the square root of 3x minus 2. This all is my second term, so minus of course. I've got a 3 and an x on top, and I've got a square root of 3x minus 2 on the bottom. And all this is still over the square of what's below, so it's still over 3x minus 2 to the first. The only issue that I have with this answer is that green term having a fraction inside a fraction. We don't want that. So I'm going to take term 1, term 2, term 3. And I'm going to multiply everything by the square root of 3x minus 2. So times the square root of 3x minus 2 on top, times the square root of 3x minus 2 on the bottom. Be very careful that anytime you multiply the top of a fraction, you got to multiply the bottom by the same thing. Basic algebra rule there. Okay, so if I do this multiplication, the red term times the square root. So 2 is 2. The square root of 3x minus 2 times the square root of 3x minus 2 just makes 3x minus 2. Moving on to the green term. The square root of 3x minus 2 cancels the square root of 3x minus 2, leaving me with minus 3x. And the blue term, 3x minus 2 to the first. This is 3x minus 2 to the half. So if I'm multiplying the same base, the rule of algebra says I add the powers. 1 plus 1/2 is 3/2. And since I'm to a power that's like 3/2, I'd probably stick with fractional powers. You could also go square root of 3x minus 2 cubed. That works also. I'd rather have that than 3x minus 2 times the square root of 3x minus 2. Either this one or this one. I'd probably go with that one. And then, after doing that, the top is very easily simplified. This is going to be 6x minus 4. So y prime, in its best, simplest form, 6x minus 3x is 3x, minus 4 all over 3x minus 2 to the 3 halves power. You should expect a similar structure for that problem. Quotient rule will be necessary to be used. Just be careful that you go through the simplification process there at the end that I expect. If you stop here, you won't get full credit. You'll get most credit, but I expect you to get all the way down to this level for this problem. Number 4, find y prime if y equals this. That is, obviously, it's a chain rule issue. The structure of this is not ideal. We don't want 1 over x cubed. Anytime you have a constant over x, it's better to write a negative power for that. So I would rewrite this as y equals x plus x to the negative third to the 5th power. So that's the first thing I would do. I change the structure so that each object in the derivative, this and this, would be in a better structure for differentiation. So if I go y prime equals now, it is a power function at heart. So 5 is the power. We take x plus x to the negative third to 1 lesser power. So that's just the power rule happening there. And then I have to take the derivative of the inside, which is going to be 1 minus 3x to the negative 4th power. Be careful, negative 3 minus 1 equals negative 4. All right, you're subtracting 1. Brain here, subtraction, 3 minus 1 is 2 comes to mind, but negative 3 minus 1, you're going to add the power, so it's going to be negative 4. And again, that differentiation is easier than doing the quotient rule. Low d high minus high d low. If we did that, low d high minus high d low over the square of what's below gives me negative 3x squared over x to the 6th, which is negative 3 over x to the 4th, which hopefully we can see is the same as that. So that was a heck of a lot easier than that, so getting that to a negative power is better. But again, quotient will get you the same result. More handwriting over here, that's a 4. At this point, what's left to do is to make it prettier. I would probably multiply this 5 through that non-powered binomial. And I'd also change my negative powers back to good fractional form. So I would get 5 times 1 is 5. 5 times negative 3x negative 4 is going to be minus 15 over x to the 4th. And then this other expression is x plus 1 over x cubed to the 4th. That would be my final answer for this. And I would expect a similar structure. There'll be some fractional expression in there that can be changed to negative power. The powers will be different, whatever, but that's kind of how I want the answer to end up. Number 5, calculate y prime. This is an implicit differentiation problem because it doesn't say y equals. If I look at each term individually, that's a product, so the product rule is necessary. That is just a power function, so just do the power rule. We got another power function, power rule, another power function, power rule. So blue is the complicated one, everything else is pretty straightforward. With implicit differentiation, anytime you differentiate a letter, if the letter's x, you're good to go. If the letter's y, you have to put a dy dx next to it. So if we start with the blue term, function 1 is x cubed. So 1d2. The derivative of y is 1, but it's y, so we're going to put dy dx. So 1d2. It doesn't matter what function 1 is when I'm differentiating. d2 is a y function, so we're going to put a dy dx. Plus 2d1, function 2 is y. d1 is going to be 3x squared. That is an x function, so it's just 3x squared. All right, so we're done with that. Second term, 4x squared. Derivative is going to be plus 8x. That's an x function, so we're done. Next function is 2x, its derivative is 2, it's an x function, so we're done. The final function is y, its derivative is 1, it's a y, so we have to put a dy dx on it. So again, as you differentiate, if you do a different derivative and it's not x, you have to put the dy dx on it. So what I created here is a total of 1, 2, 3, 4, 5 terms. And of those 5 terms, those 2 contain dy dx, the other 3 don't. So I'm going to rearrange the problem now, getting everything dy dx on one side, everything not on the other. I'm going to go ahead and move the 3x squared y and the 8x over to that side. And the 1 dy dx is going to come over to this side. So everything that's staying, I've got an x cubed dy dx that's staying here. That stays the same sign. The 1 dy dx moves over, so plus 1 dy dx equals, and then we have a 2 staying over there that stays positive. This moves over, it becomes negative 3x squared y, and that moves over, becomes negative 8x. What's left then is, we have multiple terms with dy dx, so I'm going to take a dy dx out of that. The right-hand side doesn't get affected by that. Divide everything by x cubed plus 1. That goes away, and there's your derivative. I would assume a similar structure, mostly power rules, one product rule. Some things have dy dx, some things don't. Do good algebra from here down and you should be in good shape. The derivative part's not terribly difficult, so it should be one you can manage. Number 6, y equals sine of 5 theta. Know your 6 trig derivatives. Sine is cosine, cosine negative sine, tangents secant squared, cotangent negative cosecant squared, secant, secant tangent, and cosecant negative cosecant cotangent. This is a sine function. It doesn't have to be a sine function on the test. It's sine of stuff. It's not sine of a letter. So if I use the chain rule, y prime equals, the derivative of sine is cosine of the same thing. And then the derivative of 5 theta is 5. And all I can do to make that any prettier is move the 5 out in front. The main idea on that problem is know your trig derivatives, know how the chain rule works. It'll be that basic. It'll be some trig derivative of some simple function. You do the trig derivative of the same thing, derivative of the function, move it out in front. Easy 8 points. Number 7, calculate y prime. This is basically the same idea. This is a little bit more complicated function here, but it's still a trig derivative, chain rule involved, so y prime is going to be secant squared of the same thing. And then the derivative of 5x squared minus 10 is 10x. Pull the 10x out in front. A couple friendly ones right in a row like that. Know your trig derivatives. That's the moral of the story. If you do it, there's an easy 16 points. Number 8, find y double prime. Now this is a special structure. We've seen it when we did the second derivative of chapter 3.8 with implicit differentiation. We got some extra practice this week. X to a power plus y to a power equals a number. When you do a second derivative, it's just going to have a special thing at the end there that makes it really nice. But if I just start off with the basic derivative of this, x cubed plus y cubed equals 8 is an implicit function, so implicit differentiation is necessary. Derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared, but we had to put a dy dx since that's a y term. The derivative of any number is 0. So start off there. And if I want to get dy dx, I'm going to move the 3x squared over here first. So I'm going to get 3y squared dy dx equals negative 3x squared. Divide both sides by 3y squared. Leave me with dy dx is equal to negative x squared over y squared. That's your first task, find the first derivative. Once you have the first derivative, your next task is to find the second derivative. And that's just the derivative of the derivative. So if I move on to the second derivative, here's my first derivative. I'm going to write the second derivative, which is d squared y over dx squared, equals the derivative of this object, which is a quotient, so the quotient rule is necessary. So low, y squared, d high, negative 2x, minus high, negative x squared. D low is going to be 2y, but I have to put a dy dx on that. Over the square of what's below, y to the 4th. Y squared squared is y to the 4th, you multiply the 2's. Alright, if I beautify that up a little bit, I'm going to get the second derivative is going to equal, that's going to be negative 2xy squared. I've got minus minus, which makes plus. Altogether I get plus 2x squared y dy dx, which happens to be that expression. So I'm going to put that expression back in here over y to the 4th. So again, I'm differentiating. when I do the derivative of y squared, it's 2y dy dx. That's just a first derivative when I'm differentiating this. This is just a first derivative of that object. The dy dx is there. Dy dx has a value, so we substitute that value in, and we get that. That gets me to the second derivative equals, and then if I fix this up as best I can, I get negative 2xy squared. Positive times negative makes a negative, and this, and this are all on top, that's on the bottom. This cancels one of those out. So altogether I get 2x to the fourth on top, and y on the bottom all over y to the fourth. And then I'm back to this fraction inside of fraction issue that we've had already in this test. So I'm going to multiply everything times y. So this times y, this times y, this times y. Those y's cancel. So I get my second derivative is going to equal negative 2xy cubed minus 2x to the fourth all over y to the fifth. And that's the derivative. That's the second derivative there. I will give you almost full credit for that. The last thing I want you to see, and you should expect this to happen anytime, again, you have this structure. X to any power plus y to any power equals any number. What should happen is there should be a common factor here that you take out. Just basic taking the greatest common factor out that we learned in Algebra 1. Negative 2x in this case. Leaves me with y cubed plus x cubed. This is going to equal this, which equals 8. So y cubed plus x cubed equals 8. So the best answer here is negative 16x over y to the fifth. And I would expect you to get down to that level to get full credit. Out of 8 points I'd probably give you for this answer, I'd probably give you 6 of the 8 points. I expect that last step to be done, get down to the best final answer to get the full credit on that one. Number 9, find an equation of the tangent line to y equals x squared over x minus 2 at the point 39. So equation of tangent line immediately should bring to mind that the slope of the tangent line is the derivative of this function. So the function is a quotient, so the quotient rule is going to be used. So y prime is going to be low d high minus high d low over the square of what's below, which if I just beautify it up a little bit, I'm going to get 2x squared minus 4x minus x squared all over x minus 2 squared. And 2x squared minus x squared makes x squared. So x squared minus 4x on top, x minus 2 squared on the bottom. That's the slope formula for this problem. The point of tangency is 3, 9. That's x equals 3 and y equals 9. As we can see in the slope formula here, y prime, the slope is a bunch of x stuff. So I take that 3, change all the x's to 3's. So the slope of this line that we're looking for is going to be 3 squared, which is 9. 4 times 3 is 12. 3 minus 2 is 1 squared. And 9 minus 12 is negative 3 over 1 is negative 3. So I have a slope of negative 3. My point of tangency is 3 comma 9. So if I go to y equals mx plus b, there's y equals mx plus b. So 9 equals negative 9 plus b, so therefore b would have to equal 18. Slope of negative 3, y-intercept of negative 8, or positive 18, y equals negative 3x plus 18 would be the equation of the tangent line to that curve at that point. Okay. What I typically do, I check to see you did the derivative correctly, and then I check to see you get the correct slope. I check to see if you get the correct y-intercept and write the answer right. So if you do the derivative wrong, you lose some points. But if you get the wrong derivative, but then use that correctly from that point, you get full credit for everything beyond that. So if you at least get a derivative, that's worth probably 3 points. And then there's still 5 points left. You do everything else right from there. Everything else from there is just an algebra problem. So most of this problem is going to be an algebra problem. If you mess up on your derivative, if you do everything else correctly from that point, you get full credit for everything else. So just keep that in mind. Number 10, find the equation tangent line to the curve. So this one here is an implicit function, so I'll probably use implicit differentiation. I have radicals. I don't like radicals, so I'm going to change them to fractional power. So the first thing I do is take that function, 2x to the half plus 4y to the half equals 10. Create a better structure for myself. I can apply the power rule to differentiate. Again, this is an x term, so it's fine. This is a y term. I have to put a dy dx when I differentiate. So I'm going to get 1 x to the negative half plus 2 y to the negative half dy dx equals 0. Again, it's just an implicit function. Implicit differentiation is necessary. If I want to get dy dx, then I'm going to move the x to the negative half over here. So the 1 becomes negative, the x to the negative half is still negative half. I might even go this route. I might go 2 over the square root of y dy dx equals negative 1 over the square root of x. Get back to radicals in the correct positions. Negative powers belong in the denominator, half powers are square roots. I get a fractional structure here, so the square root of y over 2 is the reciprocal. Multiply the other side times the square root of y over 2. Square roots of y and the 2's cancel over here, leaving dy dx equals. And I end up with negative the square root of y over 2 times the square root of x as my derivative. And again, the derivative is just the slope formula. The point of tangency, that's x equals 1 and y equals 4. This derivative has both x and y in it, so I would substitute both numbers in to find the slope. So slope equals the square root of y, negative the square root of y, square root of 4 is 2, over 2 times the square root of 1. So the slope is going to equal negative 1. Want to know what the slope is? Again, my slope is negative 1. My point of tangency is 1, 4. I go y equals mx plus b, y mx. So 4 equals negative 1 plus b, so b therefore is equal to 5. Y equals negative 1x plus 5. The 1 is 4 correct, negative x plus 5 would also be correct. Number 11, a paper cup has the shape of a cone with a height 12 centimeters and a radius 4 centimeters at the top. If water is poured in the cup at a rate of 5 cubic centimeters per second, how fast is the water level rising when the water is 3 centimeters deep? So our initial cone, our paper cup, has a radius of 4 centimeters at the top, and it has a height of 12 centimeters. Okay, that's the cup. That's not going to change. Okay, so that's the cup is 4 centimeter radius at the top. It's 12 centimeters deep. Water is being poured into the cup. So let's get some green water here. That's kind of gross. Anyway, water is being poured into the cup, and the radius the water makes and the height the water makes are changing. Okay, so keep that in mind when you're doing a related rates problem. You have dimensions that change, dimensions that are set in stone. The cup's always going to be 12 centimeters deep, and it's always going to be 4 centimeter radius at the top. The radius of the water and the height of the water are changing as it's being poured in. All right, 5 cubic centimeters per second is a volume, so they're giving us the change in volume. So dV over dt is going to be 5 centimeters. It's being poured in, which means that the volume is increasing, so positive 5 cubic centimeters per second would be the change in volume. They want to know how fast the water level is rising, so we're trying to find dH over dt. Alright, so that tells me that probably I want to get everything in terms of h here. So first off, if we deal with volume of a cone, volume of a cone is equal to the area of the base of the cone, which is a circle, times the height of the cone, h, divided by 3. And what I'm doing the volume of is the water, because the water is forming a conical shape also. So I'm not using 4 for a radius or 12 for height here. I'm using r for the radius, h for the height, because we're dealing with the volume of the water. And again, that's got too many variables in it. It's got v, r, and h. I just want to have h and v, so this r has to go away. So what I'm going to look at with a cone is similar triangles. The radius matches up to 4, the height matches up to 12, so I know that 4 and r on top would go with 12 and h on the bottom. That gives me 4h is equal to 12r, so r is going to equal h over 3. And I want to get r equals h over 3 because, again, I'm trying to find the height, the change in height with respect to time, so I want to get r out of there. So if I take this volume formula and pi times r squared times h all over 3, that gets me pi times h squared over 9 times h all over 3, which just becomes pi h cubed over 27. That over 9 goes to the bottom. The h squared, h, and pi stay on top. So there's my volume formula relating v and h. I got my change in volume. I'm looking for change in height. I want my height equals and my volume equals. And if we look at differentiating this, that's going to go away. That's going to stick around. So the water is 3 centimeters deep. That's important to know. So at this point, I know everything I need to know. So I'm ready to go. So my function v equals pi h cubed over 27, dv over dt. Remember when we do related rates, we're going to always differentiate with respect to time. Time isn't in any of those variables, so they're all going to be over dt. So 1 dv over dt equals, and if I do this, I'm going to get 3 times 127. That's going to be pi h squared over 9. So if you imagine 3 times pi h squared over 27, that's where that comes from. And again, that's h. We're differentiating h, so it's going to be times dh over dt. What I'm trying to find is dh over dt. What I know is dv over dt and h, so I substitute everything I know. This is equal to 5. This is equal to 3. Just so happens that 3 squared is 9. Those cancel. So we're going to get 5 equals pi dh over dt. So 5 over pi equals dh over dt. And we're dealing with centimeters per second. The height unit is centimeters, so dh over dt is centimeters. The time unit is seconds, because we can see per second. So 5 over pi centimeters per second, you can get a decimal approximation for that if you wish. I'd be fine with either answer. I'm going to leave it like that, so I don't have to use a calculator. Number 12. A balloon is rising at a constant speed of 11 feet per second. A boy is cycling along a straight road at a speed of 10 feet per second. When he passes under the balloon at 65 feet above him, how fast is the distance between the boy and the balloon increasing 5 seconds later? Okay, the hardest part of this problem is setting it up properly, so let's just do that real quick. Let's make this the road that the boy is on. And let's actually bring it down a little bit. Okay, the boy is on the road, and at some moment in time, he is here, and the balloon is directly above him. Let's make that a dotted line. Okay. And the balloon is right here. And at that moment in time, at that single instant in time, that balloon's exactly 65 feet above him. Okay? Now, obviously that's changing, but that's our starting point. That's not going to change. Okay? The fact that at the moment in time when that boy was directly under the balloon was exactly 65 feet above him. At that moment in time, that's what was true. That's never going to change. All right? The boy's going to continue cycling along this path, so he's going to, let's get him a blue line. He's going to be going this way, like so. So the boy's distance from the beginning point is changing. Let's call that x. The balloon is at the same time going up, because it says the balloon's rising at a constant speed. So from this moment, the balloon's going up, and let's call that y. All right. The boy's distance is changing that way. The balloon's distance is changing that way. The distance between the two we'll call that z. These are at a right angle. What you have to realize, though, this 65 plays into it because, again, at the initial moment in time, that's where the balloon was, exactly 65 feet above. So what y represents is not how far the balloon is above the ground, it's how far the balloon is above 65 feet. That's the easiest way to handle this. Obviously, there's 3 dimensions here. We do have 2 speeds. The speed of the boy is 10 feet per second. The speed of the balloon is 11 feet per second. And if we have 2 rates, we can find a 3rd rate. So we're good to go for that. The relating equation between these dimensions is a Pythagorean theorem. X squared plus y plus 65 squared is equal to z squared. I'd probably go ahead and square that out, so I'm going to get x squared plus y squared plus 130y plus 4,225 is equal to z squared. All right, that's my relating equation. X equals something, y equals something, z equals something, and dx over dt equals something, dy over dt equals something, and dz over dt equals something. So, x. Now, it does say in 5 seconds later. All right, that's what they're telling us there. So 5 seconds later, the boy is going at 10 feet per second for 5 seconds, that's 50 feet. The balloon's going 11 feet per second for 5 seconds, that's 55 feet. Added to the 65 feet makes 120 feet. Oops, but y is 55. Sorry about that. Y is 55. This dimension's 120, but that's 55. And then as far as finding z is concerned, I'd probably go here, be a little easier. 50 squared plus 120 squared is equal to z squared. If you recall your Pythagorean triples, 5, 12, 13, 50, 120, 130 works. If you can't remember that, 50 squared is 2,500, 12 squared is 144 with a couple extra zeros. That gets me 169, a couple zeros, which is, of course, 130. All right, so take your pick. I can't guarantee a Pythagorean triple happening on the test. Those are hard to make, but in a situation like that. But if I can, I will. But x, y, and z are very easily found. And then dx over dt is the speed of the boy. The boy's distance is increasing. X is getting bigger, so it's positive 10 feet per second. The balloon is also, y is getting bigger, so dy over dt is positive 11 feet per second. And then, of course, dz over dt is what we don't know. Got my relating equation, got all my pertinent information here, so I just differentiate. I'm going to get 2x dx over dt plus 2y dy over dt plus 130 dy over dt is equal to 2z dz over dt. Keep in mind the 4225 derivative is 0, so it goes away. Pythagorean theorem, almost always everything divides by 2, which it does here also, so I would probably do that. X dx over dt plus y dy over dt plus 65 dy over dt is equal to z dz over dt. And then we're looking for this one, so we get all this stuff. I can just divide by z right here. Then I just substitute my numbers in. So 50 times 5 plus 55 times, 50 times 10. Dx over dt is 10, so 50 times 10 plus 55 times 11 plus 65 times 11 all over 130. And that's the point where I'd probably get a calculator out and work it. So 50 times 10 plus 55 times 11 plus 65 times 11 equals, divided by 130 equals, comes out to 14, that's nice, dz over dt equals 14 feet per second. I will promise you I'll have difficulty getting the one on the test to come out nice and pretty like that. So don't expect a perfect answer like that to come out, like an integer to come out. Just know that all the pertinent information you need will be findable. You'll be given the speed of the boy, the speed of the balloon. You'll give the initial position of the balloon above the boy. It should be workable. If it comes out to an integer, that's just like a bonus. I can't expect that to happen. It's not very easy to make that happen. Finally, the bonus. This is a differential problem. A window is the shape of a square surmounted by a semicircle. The base of the window is measured as having a width of 84 centimeters with a possible error measurement of 0.2 centimeters. What it tells me is x equals 84 centimeters and dx is equal to 0.2 centimeters. Use differentials to estimate the maximum error possible in computing the area of the window. So what I can see here is that x over 2 is the radius, because of course x will be the diameter. Oops, this doesn't have to be x necessarily. Oh, it did say square, yes, so that is x squared, so x. All right. So the area of this thing, we have the area of the square, which is x squared. And then we have the area of the semicircle, which is pi times its radius squared divided by 2. So the area of this thing comes out to x squared plus pi x squared over 8. That's the area of the window. And they want to know the maximum error possible, so I simply have to do the differential of A is equal to 2x dx plus pi x over 4 dx. And then I just substitute x and dx into that expression. So dA equals 2 times 84 times 0.2 plus pi times 84 over 4 times 0.2. And again, that's just a matter of using a calculator. So 2 times 84 times 0.2 plus pi times 84 divided by 4 times 0.2. I get a maximum error of 46.7947 centimeters squared.